Hi everyone, so in this video we'll discuss hidden layer activations. So basically, like to recap, a deep neural network, you have the input layer, and then there is linear transformation, and then you have the first hidden layer, and then nonlinear activation, and then linear transformation, then the second hidden layer, you have nonlinear activations, and so on. So what we mean by hidden layer activations are the non-linear activation functions that are employed at the hidden layers. So to understand how to choose the hidden layer units, it's important to understand what the role are. So you can think of them as summarizing features, right? So for example, if I have a task of classifying images, right? So I want object recognition in images. So I want to know whether the image has a human or a cat or a dog and so on. Then maybe the first hidden layer will detect edges in the image. Then the second hidden layer will make sense of shapes, and then these shapes can be composed on each other and so on, right? So that's why typically you have many hidden layers or many hidden layer units in the first layer. Like later when we'll discuss convolutional networks, you will see that you have a large number of small kernels in early layers, and then a smaller number of larger kernels in later layers, because of this intuition that earlier layers are capturing low-level features, and then later layers are capturing the higher-level features, right? So the first thing to notice is that hidden units are applied, like the output of hidden layer activations is applied to a linear transformation, right? So it's not plugged in a cost function as we saw in the sigmoid and softmax, right? So how would that make things different? It actually makes things a lot different, because the cost function or the cross entropy cost function has a logarithm in it, right? So in the sigmoid and the softmax, they have exponential, so the logarithm and the exponential cancel each other, and then you have linear behavior. And as we discussed, linear behavior is a good thing because it helps satisfying the two desirable properties in gradient-based learning, which is the gradient is consistent and doesn't saturate. So just to recap, consistent means that the direction of the gradient doesn't change by much very quickly, and doesn't saturate means that the magnitude of the gradient remains significant for a larger part of for a wide region of the parameter space, right? So these two design factors are very important for hidden layer units, is that you maintain consistency of the gradient, you maintain non-saturation of the gradient. So linear behavior is a good thing for hidden units since they are not applied directly to a cost function that has logarithm, right? Now the second property is a property that's not very well understood, but it persists in experimental results, which is sparsity. So it turns out that hidden layers that have sparse patterns, so for example, if I have hidden layer activations, they are called activations because most of these functions have what's called an activation region, like the rectified linear unit, for example, right? This is the activation region for the ReLU function, right? Or the active region, right? And then the zero is non-active. So we say that the ReLU doesn't fire if the input is less than zero, and it fires if the input is more than zero, right? So if you have, let's say, 100 ReLUs in the first hidden layer, it's typically the case that you will see only 10 or maybe only 5 of them that would fire in typical training, right? So this sparsity is not very well understood theoretically, but it seems to persist that for good networks that deliver good performance, they have sparse hidden layers. Now, so basically, because there is no theoretical justification, we will discuss the intuition behind it. So sparsity can facilitate generalization and reduce computation. Why is that? So if I have only 5 of 100 ReLU units are firing in the first hidden layer, that would reduce the number of calculations in the second hidden layer, right? This is in forward propagation. And it will also reduce when I'm calculating the gradient. We do what's called back propagation, which we'll discuss it soon in later videos. Then also in back propagation, I only need to compute the gradient of only the active units with respect to the parameters, right? So it simplifies the computation. But not only that, so what does simplifying the computation give me? It gives me that the active hypothesis space is smaller, right? So imagine I have 100 parameters. This corresponds to a 100-dimensional hypothesis space. If I select only 5, then I'm looking at a very small subspace in that hypothesis space, which is 5-dimensional, right? So now this can facilitate focusing only on that smaller subspace, right? So this is why the reduction in computation coming from. Now it's more tricky to understand the intuition of why this also facilitates generalization. By generalization, we mean that we are learning things that can transfer to examples that are not explicitly seen during training. That's usually what generalization means, is basically you are extracting concepts, right? So hold on to that idea. Later we will stress on why a sparse hidden layer pattern can facilitate generalization or reducing the overfitting, basically. Now, this is also inspired by how we think our perception works, right? So when I look at some picture, right? So we think that the way we do that is that we focus our attention on only a small part of that picture by identifying where the patterns are, right? So I see only the part that's interesting to me in that picture. Okay, now let's go back to the first thought. How does that facilitate generalization? Imagine I see the same picture of a face, and that face in multiple images, it's rotated by different angles. I wouldn't even notice it if that angle is slight, because I am focusing my attention on the important part, and that's how I see the image, right? So imagine another example that's very simple. Imagine I see on a computer screen an image of a person, and on another screen, maybe with much lower resolution, I see the same image. In many cases, even though the actual physical image is very different, right? So the arrangement of the pixels and so on is very different. I will see the same image in my mind because what I am seeing is really the concept, right? So this is why when you have these sparse patterns, you focus on the important parts so that you can generalize to identifying these important parts, even if you see them in a slightly different way at test time, right? So that has analogy to how attention works in nature. Now, are sigmoid and softmax good? Generally, no. Why? Because they have exponentials, and exponentials saturate easily, right? So there is a region where the exponential would saturate. The same thing for the log. There is a wide region where the log would saturate, right? Not only does exponential saturate in the negative side when they are close to zero, exponentials also have a non-consistent, highly non-consistent gradient because the direction of the gradient can change very quickly. But as we will see, softmax can be useful in training recurrent neural networks, and we will discuss that later. Thank you.